In this video, we're starting section 8.8 on improper integrals. Our goals are to talk about what improper integrals are and how we can recognize them. The first type of improper integral involves a situation where our interval is infinitely long. In the second type, our function has an infinite discontinuity somewhere on the interval. So a picture of that might look like I have some axes and I have my interval from a to b. And there's a vertical asymptote somewhere on the interval. So maybe that happens at an endpoint like this. It could also happen in the middle. And then my graph kind of snuggles up next to that vertical asymptote. So it gets infinitely high here. That creates that infinite discontinuity. And I want to be able to evaluate an integral in a situation like this. So after we talk about those two types, then we are going to focus on doing a bunch of examples. So in this video, we will focus on what improper integrals are and how we can recognize them. Let's first recall that when I have a definite integral, for that to be defined, I need my interval from a to b to be finitely long, and my function's got to be continuous on the closed interval from a to b. So it's got to be continuous the whole way, including at those two endpoints. It turns out that we can relax this condition a little bit. The integral is going to be defined as long as my function has finitely many jump discontinuities. And in the graph that we have here, there's a jump discontinuity at 4, because as I draw it, the graph sort of jumps from as I approach the hole here to over here. So I have a jump if the left-handed limit and the right-handed limit both equal some finite numbers, but they're just different. And that creates a jump in the graph. So when I have a situation like that, we can still work out the definite integral, but I have to split it at this discontinuity. So if I look at the left-hand side, well, that's going to be this area A1. On the right-hand side of that discontinuity, there's kind of two pieces. There's this region A2 and this region below the x-axis, A3, which I'll have to count as a negative area. So this gives me overall A1 plus A2, those are my positives, minus A3, that one's negative because it's below the x-axis. And then plugging in, this is 7 plus 3 minus 5, which just equals 5. All right, so that's how I can handle an integral in a situation like this, where there's just a jump discontinuity. Our goal in this section is to talk about integrals in a slightly more complex situation. What if my interval is infinite? So if it's infinitely long. So the picture of this would be, if I draw some axes, and I have an interval that starts at a, and imagine I have the graph of a function. And I want to know what the area is starting at a, but then going all the way out to infinity here. So if we shade that in, that region, it extends infinitely far this way. So it might seem like at first glance, well, isn't that just going to be infinite? But as we'll see when we work out some examples, sometimes this area can be finite, which is a little weird, but we'll see that when we get to some examples, and we'll talk about what that means. The other type of improper integral is, what if my function has an infinite discontinuity? So we already talked about what this looks like a little bit, but let's draw another picture. Let me draw some axes, and then I'll draw some interval from a to b. So an infinite discontinuity means I have a vertical asymptote. So maybe now I'll draw a situation where it's in the middle. So perhaps my graph does something like this, snuggling up next to the asymptote from one side, and maybe on the other side it's doing something like that. So the integral here, it consists of this portion on the left of the asymptote, which extends infinitely high. It also consists of this part on the right of the asymptote, this part on the right, and that also extends infinitely high. It kind of seems like the area should be infinite because it goes infinitely high, but we'll see some examples where this can very much be finite. Okay, so we are ready now to give a more precise definition of these improper integrals so that we'll be able to evaluate them. So first, if I'm doing an integral that starts at some number a and it goes until infinity, to be able to handle infinity and plug it in and do algebra with it, I'm going to need a limit. So I'm first going to replace the infinity with a variable like t, and then do a limit as t goes to infinity. So to be able to do this, I'm going to need this, first off, this integral, when I plug in a and when I plug in my variable t, to exist. I'm going to need that to kind of work out and be fine for every t value that's greater than or equal to a. So that just means I should kind of be able to do that integral. And then, I'll work out what the limit is. And if that limit exists, meaning if it's some finite number, then this improper integral equals whatever value that limit takes. If I have my interval starting at negative infinity and going until some number b, I can do the same type of thing. Let's replace the negative infinity with t and do the limit as t goes to negative infinity now. So with both of these, if that limit exists, we call the improper integral convergent. And if it doesn't exist, we say that the improper integral is divergent. The final situations, well, what if it's starting at negative infinity and going to positive infinity? It turns out we can only handle one of the infinities at a time, so to do both of them, I have to split up the integral into two pieces, where the first piece will start at negative infinity, and it'll go to some number a, some finite number, and the second integral will have to pick up where the first one left off. It'll start at a and then go to infinity. So a could be any number, just as long as I pick the same thing here at the top and at the bottom of the next one. Both of these integrals are improper. And if both of them converge, meaning if they're both some finite value, then this doubly infinite improper integral will exist. It'll converge and just equal whatever these two are added together. So we'll see an example of that later. Okay, so let's do some examples. Let's apply these definitions. For the first one, I want to determine whether this integral from 1 to infinity of 1 over x squared dx converges or diverges. And if it does converge, evaluate it. So our definition says, first, with those limits of integration, the one at the bottom is fine. But for the one at the top, the infinity, change it to a t, and then take the limit as t goes to infinity. So to do this antiderivative, 1 over x squared, well, first, that's just the same as x to the negative 2. Then I can do my reverse power rule. So I got the limit as t goes to infinity. And doing my antiderivative, I'll get x to the negative 1 over negative 1. And then plug in 1 and plug in t. I can simplify this function before I plug in, right? Because this is the same thing as negative 1 over x. Now let's plug into that. So I get the limit as t goes to infinity. If I plug in t, I'll get negative 1 over t. And then minus, if I plug in 1, I'll get negative 1. So I'll put a parentheses. And then this limit applies to this whole thing. So just so that's clear, maybe I'll put a bracket around the whole thing. At this point, let's try plugging in the infinity. So I got negative 1 over infinity, and then plus 1. Negative 1 over infinity, that's 0. So overall, I'm getting 0 plus 1, which is 1. All right, and we just did our first improper integral. What does the picture of this look like? Like, what does this mean visually? If I draw some axes, and then I draw the graph of 1 over x squared, it's got one piece over here, and one piece kind of mirroring that on the other side of the y-axis. So my interval starts at when x is 1, and it goes until infinity, so we're interested in this area to the right of x equals 1, which extends infinitely far. And based on the work we've just done, what we've shown is that this area, which kind of looks like it should be infinite, is actually 1. So not only is it finite, it's actually kind of small. It's just 1. And that's weird. So on a conceptual level, why is that happening? Well, it turns out this graph gets close to the x-axis so quickly that as I go further and further out, this area that I end up adding is so small that it doesn't make this area get very big at all. It stays quite small. Okay, let's take a look at another example. So what if I change my function and I now do the improper integral of 1 over x on the same interval? So the lower limit of integration is 1. The upper one, replace it with a t. So replace the infinity with a t and then do a limit. Limit as t goes to infinity. This antiderivative involves ln. So I get the limit as t goes to infinity. I get natural log absolute value of x. Gotta plug in the 1 and plug in the t. So if I plug in, I'll get the limit as t goes to infinity. And if I plug in t, I'm going to get ln of, well, so here, based on the problem, well, t is going to be something positive because it's approaching positive infinity. So when I do that, the absolute value of it I can just drop the absolute value because it's a positive number that I'm plugging in. So I can just write ln parentheses t, and then minus what I get if I plug in 1. So similarly, 1 is positive, so I can just drop the absolute values. All right, so I'm taking the limit of this whole thing. So I'll put a bracket around it. Now let's try plugging in infinity. So that'll give me ln of infinity, and then ln of 1, well, maybe let's think about the graph of y equals ln of x. Let's think about the graph of y equals ln of x. What does that look like? What does that look like? So I'll draw some axes. Just for review, let's also talk about the graph of y equals e to the x. Because if we remember the graph of y equals e to the x, ln is just, I can get it very quickly. So the graph of y equals e to the x, that looks like this. You know what? Okay, let's actually draw both of them on the same axes. Okay, so I changed my mind here a little bit. Let's draw both of them together so I can talk about their relationship. So with y equals e to the x, that one, let me move these around a little bit. So y equals ln, y equals e to the x. So y equals e to the x, that graph looks like this, my exponential growth graph, where this point here, when x is 0, and I plug that in, e to the 0 is 1. ln of x is the inverse of y equals e to the x. And it turns out that inverses are reflections of each other across this diagonal line, y equals x. So if you reflect the e to the x graph across that line, we'll get a picture like, we'll get a graph like this, the reflection of it. Where this point that was at 0, 1 has now gotten reflected, so it's at 1, 0. And one of the things that this shows us is, well, ln of 1 is 0. ln of 1 is 0. What's ln of infinity? Well, if I look at the graph, as x is going to infinity, that's this part of the graph. X gets really, really big, going further and further out. And as that happens, the y values are also getting infinitely big. So ln of infinity is infinity. That minus 0 is infinity. So because I'm not getting a finite value, we say that this diverges. So this integral diverges. What does the picture of this one look like? Well, if I draw some axes, now my function is 1 over x, and that function's got two pieces. There's one piece over here in this first quadrant, and then a mirror image now in this third quadrant. I was focused on the region starting at when x equals 1. Starting when x equals 1. Okay, and then going onwards out to infinity. And if I shade that in, let's do it in a different color. Shade it in, shade it in, shade it in. This area also extends kind of infinitely far, and based on the calculation we just did, this area is infinite. This area is infinite. So why is this happening? Because these graphs look pretty similar, especially in terms of like the area I'm trying to figure out. Well, you know, the conceptual reason is as x goes to infinity, the 1 over x squared graph, as I go really, really far out this way, it approaches, like it's getting very close to this x-axis, so it's getting very close to 0, much more quickly than 1 over x does. Because with this one, the denominator is going to get squared. The other one, it's not. So this one's going to get smaller way faster than the 1 over x does. As a result, the area under this 1 over x squared graph is significantly smaller than the area under the graph of 1 over x. And that's conceptually why this possibility could exist, even though they kind of look similar in shape, that this one's so much bigger and it could end up being infinite. So over the next few videos, we're going to do more examples of these improper integrals.